In the previous class, we considered frequency domain characterization of the random process. So for that purpose, we considered the Fourier transform of a function f of t, which is given as integral minus infinity to plus infinity f of t e power minus j omega t dt. So here, the Fourier transform of this particular function f of t exists when this condition is satisfied, or this is the sufficient condition for existence of the Fourier transform of f of t. Here we are letting x of t is a random process and small x of t is one sample function of the random process x of t. So here we define a new function xt of t, which is equivalent to x of t for the interval minus t to t. That is, we are simply truncating the sample function for the interval minus t to t. That is, instead of considering the entire function from minus infinity to plus infinity, we are letting this x of t over the interval minus t to t. So that function, the x of t over the interval minus t to t, is designated as xt of t. So this subscript t indicates we are truncating from t to minus t to plus t, and that is 0 otherwise. So therefore, the Fourier transform of this function is equivalent to this much. Here, the assumption is this particular function xt of t is absolutely integrable over the interval minus t to t. So therefore, the Fourier transform of this is minus t to t xt of t e power minus j omega t dt. But we already know that for this interval, this xt of t is equivalent to x of t. Therefore, this integral can be replaced by this, and that is nothing but xt of omega. So this is the Fourier transform of xt of t, with the assumption that this xt of t is absolutely integrable over the interval minus t to plus t. So here, the energy content of a particular signal xt of t is given as this much, and that is equivalent to minus t to t mod x of t whole square dt, because this xt of t is equivalent to x of t from minus t to t. But according to the Parseval's relation, this can be equated to 1 by 2 pi minus infinity to plus infinity mod xt of omega whole square d omega, where this xt of omega is the Fourier transform of the function xt of t. So once you know the energy content, we can evaluate the average power. So the average power of xt of t is equivalent to the p average, that is Et divided by 2t. So we are dividing the energy with the time duration. So therefore, so this is equivalent to this much, and that can also be written as this. Here bring this 1 by 2t inside, then we can write this p average is equivalent to 1 by 2 pi minus infinity to plus infinity mod xt of omega whole square divided by 2t d omega. So here, this is the average power of the function xt of t. That is, the average power of x of t over the interval minus t to t. But here, the sample function duration may be from minus infinity to plus infinity. So that's why, if you let this t is tending to minus infinity, then we can get the average power of the entire sample function. Follow? Therefore, the average power of the entire sample function can be obtained by simply letting t is tending to infinity. Let t tends to infinity. We considered only one sample function, is it? But we already know that the random process is the collection of the sample functions. We considered only one sample function. If we take another sample function, what will be the p average? Will it be the same or will be different? That is, the p average of the second sample function may be different from this. The p average of the third sample function may be different from this. That is, the value of this particular p average varying randomly. It depends on the sample function that we consider. Because as the sample function don't take the same values. There is some variation from one sample function to another sample function. That is the values that are taken by one sample function to another sample function. So definitely this P average varies from sample function to sample function. This is the P average for one sample function. But actually we have to find the average power of the random process. Instead we obtain the average power of one sample function. So how can we find the average power of the entire random process or for all the sample functions? So for that purpose, as this particular P average varies from sample function to sample function, we can let this particular P average as a random variable. Follow? So this P average can be considered as a random variable. Why? Because for the first sample function, this P average is some value. For the second sample function, this P average value will be different. Similarly for the third, fourth and so on. Then once you consider this particular P average as the random variable, then the average power for the interval minus t to t for the entire random process can be obtained by simply taking the expectation of this. This P average indicates the average power of one sample function over the interval minus t to t. But from sample function to sample function, this P average value varies. So that's why we are letting this P average is the random variable. Now if you find the expectation of this particular P average, that indicates the mean value of the random process x of t, or the mean value of all the sample functions over the interval minus t to plus t. Understood this? So let this is one sample function. Here we consider the path of this particular sample function. So over the interval 2t, is it? Minus t to plus t, is it? So over this interval we obtain the P average, average power of this particular sample function over the interval minus t to plus t. Now if you consider another sample function, so over the same interval, if you find the average, so if you let the P average of this particular function is this, and the P average of this is this, let it be 1, this be t, are the same, this value and this value, definitely they will be different. So that's why the value that taken by this is different from this. So therefore, this P average can be considered as a random variable. Now, if you take the expectation of this particular random variable, let P average is the random variable that takes the values P average 1 for this and P average 2 for this and so on, P average n. So these are the values that are taken by the random variable P average. Now if you take the expectation of this, that is the mean value of this particular random variable P average, that indicates the mean value of all the sample functions or the mean value of the random process x of t over the interval minus t to plus t. So here if we take the expectation of this particular P average, 1 by 2t integral over minus t to plus t. Here we have mod x of t whole square dt. Is it right? And this is also equivalent to expectation of this, and this is also equivalent to expectation of 1 by 2 pi integral minus infinity to plus infinity is a mod xt of omega divided by 2t. Is it? So therefore, this expectation of P average can be written as, see here we can change the order of expectation and integration. This will be equivalent to 1 by 2t, so minus t2 plus t. This is expectation of mod. This can be written as x of t whole square. Why I have written like that? See, I replaced the small x of t with capital X of t. Now, this indicates the entire ensemble, is it? We are taking the expectation that is not for one sample function. This is for the entire random process. So therefore, you can replace this x of t with capital X of t, and which is also equivalent to, so 1 by 2 pi integral minus infinity to plus infinity, the expectation of xt of omega whole square divided by 2t d1. Understood this? See, this is the mean value of the random process over the interval minus t2 plus t, is it? Understood? Then how can you obtain the mean value over the entire interval? So for that you simply let t is tending to infinity. Then limit t tends to infinity. So expectation of P average is equivalent to limit t tends to infinity. So 1 by 2t minus t2 plus t. This is expectation of mod x of t whole square dt, which is equivalent to limit t tends to infinity minus infinity to plus infinity, expectation of, so xt of omega whole square divided by 2t d1. Is that right? So this last integral can also be written as integral minus infinity to plus infinity. I think 1 by 2 pi is there. So 1 by 2 pi, and this is limit t tends to infinity. Just I brought that limit inside because we can interchange the order of integration and limit. This is expectation of xt of omega whole square divided by 2. Here, don't think that this is equivalent to 0. Here, we have to substitute this limit. First, find the expectation of this, and then integrate with respect to t, divide with 2t, and then substitute the limit. Don't directly substitute the limit here. Don't think that we have t in the denominator, and as t tends to infinity, this becomes 0, and this also becomes 0. We have to substitute the limit. See, first we are finding the expectation of this, and then integral, divide with 2t, then apply the limit. So if you apply the limit before doing all these things, you will get 0. So that's why apply the limit after performing all these operations. So here, this particular quantity, expectation of P average, indicates the mean value of the random process x of t, and this is equivalent to the time average mean. What this indicates? See, we are averaging in time, so this is also called as the time averaged mean value of the random process x of t. Understood? So here we are interested in the quantity limit t tends to infinity. So expectation of mod x of omega, so xt of omega whole square divided by, is it? So this particular quantity is called as the power spectral density or power density spectrum of the random process XOR. Power spectral density or power density spectrum. So this is the characterization of the process in the frequency domain. So what this xt of omega indicates, it is the Fourier transform of the sample function for the interval minus t to t. To find the expectation of that, expectation of the square of that, divide with 2t and then take limit t is tending to infinity. So this particular quantity, see, t is constant, so this is the function of omega, is it? So therefore the Sx of omega is also a function of omega. So this is the notation of the power spectral density, and that is defined as limit t tends to infinity this much. Understood this? So therefore, once you let this quantity is equivalent to this much, can I write this as limit t tends to infinity 1 by 2t integral minus t2 plus t expectation of mod x of t whole square dt is equivalent to limit t tends to infinity, otherwise so 1 by 2 pi integral minus infinity to plus infinity. See, here we have limit t tends to infinity this much, so that can be written as, is it correct? In the above equation we are substituting this. Here this quantity is the area under power spectral density. So area under power spectral density divided by 2 pi is equivalent to the average power. What is this quantity? This quantity indicates the average power of the random process, time average power. Can I write this as limit t tends to infinity, so 1 by 2 for 2t, so minus t2 plus t, expectation of mod x of t whole square. If you let x of t is the real, this can be written as expectation of x square of t dt. What is the expectation of x square of t? Expectation of x square of t is equivalent to what is the expectation of x square of t? Is the mean square value. Mean square value is equivalent to autocorrelation function at tau equivalent to 0. So therefore, is expectation of x square of t. If you let x of t is real random process, expectation of mod x of t whole square is equivalent to expectation of x square of t. Expectation of x square of t is equivalent to Rxx of 0. So this implies, see, what is Rxx of 0? It is a constant. So that can be taken out, and the remaining term is 2t divided by 2t is 1. So limit t tends to infinity 1 is 1. So this is equivalent to 1 by 2 pi integral minus infinity to plus infinity. Is it right? The expectation of x square of t, that is the mean square value of the random process. is equivalent to Rxx of 0, that is equivalent to this much. That is, if you know the power spectral density of the random process, find the area under power spectral density, divide with 2 pi, you will get the mean square value. What do you mean by mean square value? Mean square value is nothing but the power. Indicates the power. I will modify this equation. So here we have Rxx of 0, that is equivalent to 1 by 2 pi, so minus infinity to plus infinity, power spectral density so can I write this as limit tau tends to 0, 1 by 2 pi integral or minus infinity to plus infinity Is it right? Let tau is tending to 0, we multiply with e power j omega tau. Again you will get the same. So what this Rxx of 0 indicates? Rxx of 0 is the Rxx of tau when tau tends to 0. Is that right? This equation can be written like this. Now remove that limit and we can write it as minus infinity to plus infinity e power j omega tau, sorry, d omega is there. Is it clear to you? 1 by 2. This indicates the inverse Fourier transform of Sxx of omega. That indicates the inverse Fourier transform of power spectral density is equivalent to autocorrelation function or Fourier transform of, if you take the Fourier transformation on both sides, Fourier transform of Rxx of tau will be equivalent to is it right? The inverse Fourier transform of power spectral density is autocorrelation function. So Fourier transform of autocorrelation function is power spectral density. Okay. So this equation equivalent to minus infinity to plus infinity Rxx of tau e power minus j omega tau d. Is it right? This is the inverse Fourier transformation and this is the Fourier transformation. The inverse Fourier transform of power spectral density, that is equivalent to autocorrelation function. The Fourier transform of autocorrelation function is equivalent to power spectral density. So here the power spectral density and autocorrelation function are forming the Fourier transform pair. Is it clear? So this relation is the well-known Wiener-Khinchin relation. So that is the relationship between the autocorrelation function and the power spectral density. See, we define this as the power spectral density. Is it? The power spectral density is equivalent to limit t tends to infinity, expectation of this divided by 2t is called as the power spectral density, and that is denoted as this. We can also call this as PST, power spectral density. So it is the quantity that indicates the density of the power with respect to frequency, or distribution of the power of the random process with respect to frequency. Understood? What are the units? Here, this particular quantity f of omega indicates the distribution of the amplitude and phase of this particular function f of t with respect to frequency. So this we call as the spectrum. Is it? F of omega is the frequency spectrum of the function f of t. Is it? Is it right? So what is the unit of this? If you let this f of t as a voltage function, the units are volts per H or volt per radian per second. So that is the unit of this. Now tell what is the unit of this? Power spectral density. What is the unit of this? It's a watt per H or watt per radian per second. There we have voltage, but here we are squaring it. So V square divided by some R. Here, if you let that is the normalized resistor, so V square per ohm. V square per ohm can be written as the watt. So it is a watt per H or watt per radian per second. That is the unit of the power spectral density, which indicates the density of the power or distribution of the power with respect to frequency. See, the Fourier transform of a function is also called as the power spectrum, spectrum of the function that indicates the distribution of the amplitude and phase with respect to frequency. So that's why the unit of that particular f of omega is equivalent to volt per radian per second or volt per H if you are representing the spectrum with respect to frequency. Here it is watt per H.